In this video, I'm going to talk about various operations with vectors. So I'll start with vector addition. Algebraically, the way we add two vectors is we start with their component forms, and then we just add component-wise. So the vector 1, 3 plus the vector 2, 2 gives us the vector whose x component is 1 plus 2, or 3, and whose y component is 3 plus 2, or 5. Okay, so to add two vectors, you just add corresponding components. Okay, so here's the formula that I just described. Okay, we also have a couple of geometric approaches to vector addition. So let me start with the parallelogram rule. So here's our vector, our first vector and our second vector. We want to add these two. The resultant vector we're going to get by forming a parallelogram with the two vectors we're adding. So we're going to take this first vector here, put it here, and the second vector here, and put it here, and that's going to give us a parallelogram. So here I've formed the parallelogram with the two vectors that we're adding, and then the resultant vector, or the sum of those two given vectors, is just the vector which is the diagonal of the parallelogram. So it's this vector right here, which is the resultant vector. So you can see that the vectors we were adding were the vectors 2, 2, and this vector is 1, 3, which are precisely the vectors that we're adding up here, and we know that the resultant vector is 3, 5. And that's precisely what the vector here, which is the diagonal of that parallelogram, is. Okay, so the parallelogram rule for addition of vectors, is we form the parallelogram using the two vectors, and then the resultant vector is just the diagonal. Okay, so here I've written the instructions for using the parallelogram rule for vector addition. Okay, try this example right here. Draw the vector u plus w using the parallelogram rule. Okay, the first thing we're going to do is form the parallelogram by putting w right here and u right here. Okay, so I tried as carefully as I could to make this vector be equivalent to this vector u. Okay, so it has the exact same magnitude and the exact same direction, and same with this vector right here. So it's equivalent to the vector w, only placed right here. So that's how we form our parallelogram. And then u plus w is the vector which is the diagonal. So here we have the resultant vector. All right, there's another rule we have, another way of viewing vector addition geometrically, and that's using a triangle. Okay, so here's how the triangle rule works. So I have this vector u, and I want to add the vector v to it. I start by taking the vector u, and then I take the vector v, and I put the tail of it right at the head of the vector u. Then the vector u plus v is this side of the triangle. Okay, so we take the vector u, put the tail of v at the head of u, and then we draw the vector that goes from the tail of u to the head of v, and that's the vector u plus v. We can also see that over here in the parallelogram. So here we have our vector u. Recall that this here was a vector w, and we can see precisely that the diagonal of this parallelogram, we can view it just in terms of the triangle, and we see that it is the third side of the triangle. Okay, so just to recap, we take the vector u, put the tail of v at the head of u, and then the vector u plus v has the tail at the tail of u, and the head at the head of v. Okay, so here I've written the rule for you. Okay, here's a fun application of adding vectors geometrically. So we have an aircraft that maintains a constant airspeed of 490 miles per hour due south. So that's represented by this velocity vector v sub a. And then we have a wind blowing, and it's represented by the velocity vector v sub w. So we know that since the wind is blowing on the airplane, it's actually going to change its actual course relative to the ground. So the actual velocity vector of the aircraft relative to the ground is the vector va plus the vector vw. In this case, it's easiest to get that resultant vector by using the parallelogram law. So let's go ahead and draw the parallelogram formed by these two vectors. Okay, so then the actual velocity vector of the aircraft relative to the ground is simply the diagonal of this parallelogram. All right, so here's that velocity vector. I just think this gives us a neat way to visualize what's actually happening when wind does, or one of the things that happens when a wind does act on an airplane. All right, the next operation I'm going to talk about is vector subtraction. So vector subtraction is very similar to vector addition. In fact, we can view this as vector addition if we write this as in that way. Okay, so we have the vector 1, 3 plus the negative of the vector 2, 2. So what we do is we take the first component of each, so 1, and then we subtract 2, so we get negative 1, and then 3 minus 2 gives us a 1. Okay, so the vector 1, 3 minus the vector 2, 2 is the vector negative 1, comma 1. Again, so to subtract one vector from another vector, we subtract component-wise. Okay, just as another quick example, the vector 3, 8 minus the vector 1, 1 is the vector whose x component is 3 minus 1, and the y component is 8 minus 1. All right, let's look at the geometric representation of the vector u minus v. So here we have the vector u, and we have the vector v. Geometrically, the vector u minus v is the vector that we get by going to the tip of v, so that's its tail, and its head is at the tip of u. Okay, so here's the vector u, here's the vector v. The vector u minus v starts at the tip of v and ends at the tip of u. All right, let's see why this is true. So the way I'm going to view the vector u minus v is as a vector u plus the negative of the vector v. And then since I can switch the order in which I add numbers, well, I can switch the order that I add numbers, I can also switch the order that I add vectors. Okay, so this is equivalent to negative v plus u. Okay, so the effect of putting a negative in front of a vector is that the magnitude stays the same, except the direction is in the exact opposite of the original vector. Okay, so since v is pointing in this direction, negative v is going to point in this direction. Okay, now we just get to use the triangle rule to find this sum, negative v plus u. So we start at the tail of negative v, which is right here, and then we go to the tip of the vector u. Okay, so remember that was the triangle rule. So the vector negative v plus u is this vector right here. Okay, so this is the vector negative v plus u, or we can write it as u minus v. Okay, why don't you try this problem on your own? Draw the vector u minus v. Okay, so here's the vector u, and here's the vector v. the vector u minus v. To get that, we go from the tip of v to the tip of u. All right, the last operation I want to talk about is scalar multiplication. So it's just multiplying a vector by a number. To do this operation, we just take the number, the scalar, and we multiply it to each component. So it's 2 multiplied by 3, and then 8 multiplied by 3. Okay, why don't you press pause while you work on these 3 examples. Okay, for the first one, you should have gotten the vector 2, 4. If we graph that vector, we get exactly this arrow right here. Let's compare it to the original vector, 1, 2, which is what we multiplied by 2. Okay, the vector in blue here is the vector 1, 2. So we can see that the result of multiplying that vector by 2 was that it had the exact same direction, except it was stretched. Okay, for the next vector, you should have gotten the vector 1, 2. So we started with the vector 2, 4, which we have from our previous example is all the way up here. After multiplying it by 0.5, we ended up with the vector 1, 2. So we see here, and then in this case, since we multiplied the vector by a fraction, we ended up by shrinking the vector. Okay, so if you multiply a vector by a fraction of 1, you shrink the vector. If you multiply a vector by a number greater than 1, you're stretching the vector. In both cases, the resultant vector is pointing in the exact same direction. It just has a different magnitude. Okay, this is what you should have gotten for the last example. The negative 3 times the vector 1, 1 is the vector negative 3, negative 3. So that's the vector plotted in red here. So we can compare it to the original vector 1, 1. So we see this is the direction that 1, 1 is pointing. And because of this negative right here, the vector negative 3 times 1, 1 is pointing in the exact opposite direction. Okay, so the fact that the vector is pointing in the opposite direction is due to the negative sign. The fact that it's longer than the original vector is due to the 3 here. Okay, so if we multiply a vector by a number bigger than 1, it stretches it. If we multiply it by a number between 0 and 1, it shrinks it. If we multiply by a negative number, it puts it in the opposite direction, and it either shrinks or stretches based on the magnitude. Okay, so this summarizes that little discussion. Okay, why don't we end on this example? Press pause while you work on it. Okay, so we want to multiply the vector v by 2, the vector w by 4, and then subtract those answers. So we get the vector 6, 2 minus the vector 8, negative 12. And that is the vector negative 2, comma, positive 14. Okay, we have 2 minus a negative 12, which is a positive 14.